Cool. So I hope everybody is very excited now that deep learning has started in the class. And did you guys get to look at the lecture of this week? Whatever sir taught?
Yes.
Great.
Yes. Yes.
Great. So yeah, I'm sure you'll have a lot of fun because deep learning is yeah, it's difficult to understand, but it's really fun to see how a machine can do so many things. So yeah, I mean, just your learning has just started, so be patient. And my advice would be to go ahead and try to understand everything as sir teaches, because it's really crucial that you understand everything. It's not very simple, not very trivial, but yeah, I'm sure you'll have a lot of fun in the process. So okay, let's start. Right. So yeah, so today is the fourth week and the last live lecture of the fourth week, and so we'll go through some of the very basic stuff for deep learning knowledge. So what do we want to do in machine learning or deep learning? What we want to achieve is that we are given some data, right? And maybe some knowledge about it, like some labels or something like that. And we want to basically, it's like how a child learns. So whenever you are, suppose, teaching a child alphabets or something, you draw those alphabets for that child, and then you tell them that this is A, this is B, this is C, and so on. And then the child somehow manages to learn these alphabets on its own. So this is something that we want to utilize, I mean, do for the machines as well, so that the machines are able to learn, so by the same concept. So what we want is that given some data, we want to learn from it. We want to learn what is there in the data set. If it's a classification type data where you need to, for example, classify things, like I said, like given the picture of A, you have to classify what is the alphabet. So whenever you have things like that, so all those things we want to teach the machine. We want the machine to do those stuff as well. So neural networks, yeah, these are the state of the art methods now for so deep learning and neural network for, again, learning what is going on in the data. And so now today we'll begin with perceptrons. Perceptrons are basically the building blocks of neural networks. So yeah, so perceptrons are building blocks of neural networks, and so we'll see basically what is the neural network made up of and how is it trained, right? And then at the end, we'll try to see a two-layer neural network with some coding examples. So, so what is a perceptron here? So as I said, it's a building block uh, of the neural network. So what's going on here is that, suppose you have a data, some input data, suppose some image or some text. Text means suppose a sentence or something like that. And you have basically, you convert that input data into a vector. So x0, x1, x2 to xn, this is a input vector of one image, suppose, or one sentence. And what you want to do is, there is suppose a label attached to it. So this label is given by y belonging to 0 comma 1. So this is a binary label, binary y, because there are only two labels. So suppose, as an example, you can think of what is a good binary classification example. Suppose you have been given a image of a person, and you want to see if you want the machine to learn whether that person is smiling or not. So here, smiling will be 1, and not smiling will be 0, something like that. Or you want to classify whether the person in the image is a male or a female. So again, you can assign male to 0, female to 1, something like that. So that is what we mean by classification, and this is binary classification where you only have two classes. So, what you generally, the how this is formulated is something like this, that you how you learn the mapping from this vector x to this binary class y is through some parameters called weights. So you have, it's like this, that take every element of the vector x. So it's like x0, x1, x2 to xn, and you'll attach some weights w, sorry, here, sorry, not x0, let's start from 1. So x1, x2, dot 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 xn. What you want to do is you want to learn something called parameter, which we generally represent by w's. So you attach this x1 with this w1, x2 with this w2, xn with this wn to learn something called a function g. So how will g look like? It's very simple. So g of x, where x is the input vector, is basically a weighted sum of these individual elements. So it's like wi into xi summation over I equal to 1 to n. So now this w is what you want to learn. So based on, so what is your end goal? You want to map from this input vector x to a value y. So that is what you are trying to do through these w's. So you should learn w's in such a way that you should get the value of y from such a this kind of a formulation. And there's a bias term attached with this weighted sum. This kind of gives you some class wise information. So this bias term is also there. So the output of this perceptron is this function called g of x, which is equal to the sum of the weighted sum of xi's, where the weights are all given by wi. So now, as I said, what will be given to you is this x. The data is always with us. That is represented by x, or the xi elements of the vector x. What you need to learn is this part, this wi part, which will make the model understand like how to set. The process is that you have to learn. You have to make the model learn how to set these wi's in such a way that you learn a mapping from here to here, right? So now what happens is what happens is something like this, that you have a, so you have computed this g of x. So now you want to how to move from this g of x to some label value. So the label values are either 0 or 1. So it can be something like this, that suppose you have calculated your g of x. Now if your g of x is greater than equal to some threshold theta, then you predict that your y is 1 for this particular vector x. Or if it's less than some threshold theta, then you predict 0 for this particular x. Similarly, uh, so so um, so this is how the classification happens. So we call this functionality, we call it as x. We call it as f, where we compare with a threshold the g of x value, and based on the threshold we assign the labels, the predicted labels. So this is how given some input data, you predict what is the output label.
Ma'am,
Yeah.
uh, is it necessary that sum of weight should be equal to 1?
No, there is no constraint like that here. But yeah, you have to. So this is something that you have to learn. But yeah, as of now, there is no constraint like that. So if something like that comes up, that might come up in the future classes. But for now, assume that there is no such restriction.
Okay, thank you.
Yeah, you'll get to know. Some restrictions will be there, obviously, but let's see how it goes. Okay, so one thing that we have to think of is that, so we learned now that g of x should be greater than equal to some theta for the final label to be 1. Now the problematic thing is this theta. How do we set it? Do we set it to be 0.5 or 1 or what? So that is one problem, and this is very very problem dependent, as to, or maybe even model dependent, how to set this theta. So that is why people have thought of this, that okay, since we are already learning the W's, why not learn the theta as well? Theta means what? Theta is the threshold based on which you do your classification. So what you can do is you can learn even these threshold values. So what you can do is you can convert this into this formulation. So y equal to some f of g of x equal to 1 if g of x minus theta greater than equal to 0. So just all you have to do is bring this theta to this side for both the cases. So that is what is written here, that if g of x minus theta is greater than equal to 0, then it's 1, otherwise it's 0. So now if you see, it's like what you have here is some so it's almost very similar here to if you do the mapping. So what people do is they take b equal to minus theta to give this formulation. So basically it's like summation of I equal to 1 to n wi xi, and then you give a set a minus theta, and that does the trick. So I mean that is the same formulation as this one. So now what you do is b equal to minus theta we have set. So now minus theta can be written how? 1 into minus theta, that is equal to minus theta only. So now let's do this, that let's call x 1 equal, I mean some, let's represent this one using some variable x0 and this minus theta using some variable w0. So now what will happen is, to in order to achieve this wixi plus b, how we can represent this? So this is summation I equal to 1 to n wixi, and b is minus theta, and you have already defined this minus theta as x0 w0. So this is I equal to 1 to n wixi plus w0 x0. So now you can rewrite this formulation to something like this, where g of x equal to this summation. So here note the summation starts from 1 here, and this here it starts from 0. This is just some notational, there's some notational advantages to it, where x0 equal to 1 and w0 equal to minus theta. So basically what you have done is you wanted to learn the theta, so now you have compressed everything into a single summation weighted sum like this using this formulation. So that is the advantage of this formulation. And now so obviously since theta was a learnable parameter, you have already put that into this summation. So overall we were already learning w1 to wn. Now we are also learning w0 in this formulation. Yeah. So now what is your goal? What do we want to achieve here? One thing that we want to do is, suppose you are now here, we had been given two classes, right? 0 and 1. How do we separate these two classes of data points? We want to learn a hyperplane, or a, maybe suppose you consider only two dimension for now. So we want to find a line on the suppose what do we call it, on the Cartesian plane, such that you divide the input space in such a input space in two halves, basically as it's written here. So suppose this is the line this is a line basically, and suppose there are class 0 data points are here and class 1 data points are here. So you want to learn a straight line between them that basically separates these two classes of data points. If you plot them, so suppose, as I said, that these are all vectors. So suppose you consider only two dimensional vectors x1 and x2, right? So suppose this is the Cartesian plane, and whatever so you have to learn a line in such a way that all the points that belong to class 0 are on this upper side of the line, and all the points that are belonging to class 1 are on the lower side of the line. That is how we want to separate. So this line, the usefulness of this line is that it's very easy now. Given once you learn this line, whenever a new data point comes up, suppose some z, okay, whose coordinates are z1 comma z2, it will be very easy. So if z1 comma z2 is suppose somewhere here where I'm pointing my mouse. Yeah. So suppose somewhere here where my laser pointer is, then we know that it already belongs to class 0, because we already saw from the training data that class 0 elements are on the upper side of the I mean line. So this is, I mean, this is when you consider only two dimensions, it's simpler to understand because it's a straight line then. Otherwise, when the dimension increases, suppose 1000, 10,000, anything, what you get is a hyperplane. So but the idea is same, that you, since you have only two classes, you want to learn a line, you want to plot a line, basically learn how to plot a line on the Cartesian plane or whatever plane, such that one of the classes lies on one side of the line and the other class lies on the other side of the line, right? So now a few things about, let's try to make sense of this line. So suppose, yeah, so again, if you look at the definition of of this particular g of x, you'll notice that it's the equation of a straight line, basically. And so what about the points that are lying on top of this line? For them, what we see is that this equation holds. So you have a, so this is basically what, this is basically nothing but the dot product between the vector w. So if you take this thing to be a vector 2, so this w0 to wn, and x0 to xn is another vector, then this stands for the dot product of um, um, the dot product of w and x. That is what is given here, w transpose x. And for because this is the equation of a line, whatever points lie on this particular line, for them this will satisfy w transpose x equal to 0, right? So now let's expand this a little bit more. Let's expand this a little bit more. So what is W transpose X? W transpose X is nothing but, if you think of the dot product rule, it's basically norm of W into norm of X into cosine of some angle alpha. So this angle alpha is between W and X. Both are vectors. So now what we found is, for the x's that lie on the line, this turns out to be 0, right? And now what this means is that this w is a norm, this x is a norm, so they can't be 0. So the conclusion that we reach is that cosine of alpha must be 0. When is cosine of alpha 0? When alpha equal to 90 degree, right? So when alpha equal, so alpha is, so now we have established that alpha is equal to 90 degree for points that are lying on the line. So one thing that from here, so one, the conclusion that we can draw, what is the conclusion? Conclusion is that the w vector is normal to the line that we, the this line is basically called the decision boundary. So this line that we wanted to draw for basically separating the two classes, the w vector is orthogonal to that. Fine. So now that we have established this fact that this w is orthogonal to this line that we want to find. Now let's see. Let's make some other. Let's see what else happens over here. So suppose. So since we have two classes here, 0 and 1, suppose we call one of them the positive class. Suppose y equal to 1, when y equal to 1, we call it the positive class, otherwise it's a negative class. So suppose we have taken such an example of x where it belongs to the positive class, that is the corresponding y is equal to 1, right? So now what we want is w transpose x should be greater than equal to 0, right? So suppose a positive, yeah, so correct. So W transpose X should be greater than equal to 0 for the positive classes. So if that is true, then W norm, so again we break W transpose X to norm of W into norm of X into cosine cos of alpha. Again that should be equal to 0, greater than equal to 0, which means again that cos of alpha should be positive. And when is cos of alpha positive? When alpha is again, either in the first or the fourth quadrant. So thinking of the first if we think about the first quadrant, then alpha should be less than equal to 90 degree. Similarly, for the other case, what we want is W transpose X should be less than 0 if it's a negative class, basically. So in that case, similarly we can show that alpha is greater than equal to 90 degree for those cases. So alpha, which means that it either lies in the second or the third quadrant. If you think of the map of, I mean the cosine curve, then you'll realize that this is true. That cosine of an angle is always positive when the angle is in the first and fourth quadrant, and negative when it's in the second or third quadrant. Okay, right. Yeah. So if we think of it in this way, then when will, I mean, given this line and this W, when will a new point X, suppose some X hat, suppose, when will it be positive? When it has an angle of less than equal to 90 degree with the this weight vector W, which means in this area it will be positive, and in this area it will be negative, as is given by this particular formula. So that is why we want to set it in this way. I mean, that is how the angle turns out to be. Okay, so now how does learning in such this kind of a neural network happen? So till now I've been going on about what are the weights, and what how you want to separate the data points when they belong to binary class, I mean two classes, how you want to learn how I mean the fact that you want to learn a line to separate them. So these are all fine. Now the interesting part is that these initially these numbers are all random, so we do not know what they mean, we do not know what they contain, they are just random numbers. But now that we know what we want to achieve, we want to learn some sensible values in this for these numbers, for these variables. So w0 to wn, we want to learn something that will be useful to us. And how that is done is basically through something like this. I'll just hide it. Okay. Yeah. So what happens is when I mean so as I said, we want to achieve something like this, that W transpose of X should be greater than equal to 0 when you have a positive point. But now that your W's are all random in nature, you do not know what will happen with a random W and your X. So it might be, if the W's are such that for a positive point, this W transpose X is greater than equal to 0, we are okay. Otherwise, problem happens when the opposite happens. So W transpose X is less than equal to 0, less than 0, but X is a positive point. That is when we have to correct W, because we know that W is not suitable for us. Similarly, for the negative case, suppose you have a negative point uh, where y equal to 0, but your W transpose X is turning out to be greater than equal to 0. That means what? That your W that you have learned, the W that is there with you, that is not enough. That we have to learn something more. So that is why if something like this happens, so X at any time step t, suppose, or any tth data point which is positive, but when you do a W transpose X of t, it's turning out to be less than 0, then we need to change W. We cannot proceed with the same W with I mean again, I mean we cannot proceed with the same W, so we need to update it. And what we need to achieve is that, suppose we learn a new set of weights W new, and this W, so this W new transpose of X of transpose X of t should be greater than equal to W transpose xt. That is what we want to achieve, because we already have this kind of a condition that this constraint should be satisfied for the W's to be good enough, right? So how do we satisfy this kind of a condition? So suppose we set W new equal to the old W plus your X of t. Okay, whatever X of t you have at the as the tth data point, you just add that with your old W and take that to be the W new. So let's expand this a little bit more. So what we want is this quantity. So W new transpose xt. And now we'll expand w new. So w plus xt transpose xt. So w, so here this becomes w transpose xt plus x transpose xt, which is nothing but the L2 norm of xt. So now L2 norm of xt is definitely always positive, right? Because unless x is 0, but we'll assume here that x is not 0. So for a non-zero x, this quantity is always positive, which means what? That this w transpose w nu transpose xt, whatever we found, that is definitely greater than w transpose xt, because see here, this is w transpose xt, which was our old value, and we have added something positive to it. So this relation now, so the conclusion of what I said is that if we set w new to be this value, then we have a new w new transpose xt is greater than the old w transpose xt. So this is what we wanted to achieve. So now, if you look at it a little bit in a little bit geometric sense, what we want to do here, suppose we learnt a line, some line like this previously, or suppose in the starting point, based on our w's, we were able to draw this particular line. So now, suppose you, as I said, that our w vector is normal or orthogonal to this line. So this is my w, right? And now you have suddenly found a point, data point xt, which is positive. But as I said that the positives will be here within 90 degree, and the negatives will be here on this side, right? So what, based on this line, you can see that there should not have been a positive point here in this area, in this side of the line that you had learned, which means that the line that you have learned is not yet fully correct. You need to update it a little bit. So that is why this updation happens. So based on the w that you had learned that was not working out, so you have come up with a new w, and the new, with the help of the new w, you see that suppose your new hyperplane or new line becomes somewhere shifted like this. So now if you can take into consideration your new w and this particular line, you'll see that this positive point is falling on the right region. So it was supposed to fall at a, I mean, on this side of this dotted line. So it has correctly fallen on the right side of the dotted line. So that is what is, updating about. I mean, that is how we update. So we start with a random w, and it's bound to make mistakes. It's I mean, it will basically what we in machine learning terms, what we call misclassify. So it will misclassify positive points to be negative points and negative points to be positive points. And what you want to do is update this w in such a way that your line is correctly placed on the plane, because you are starting with something extremely random, and now you are little by little you are teaching it, you are making it learn like how to place the line correctly in such a way that all the points are separated properly. So that is,
Uh,
yeah,
Ma'am, a small doubt.
yeah,
Yeah, ma'am, here we are only trying to learn W and we are trying to shift W based on our requirement.
right, right,
And the actual line will be automatically shift.
correct, correct,
But ma'am, how it is possible? I mean,
yeah, yeah. So
there can
based,
be multiple lines which is orthogonal to W.
no,
So
so
which line?
based on this equation, you will get the line. This is the equation of a line. So these are all what to say. These are all this is a some n-dimensional vector, and when you do this, when you have this equation, sorry, this one particularly. So this is the equation of a line. So once you have the correct w's, you can draw the line. That will not be a problem. So it's like this. So suppose, what is the equation of a line? Mx plus y equal to mx plus c. So suppose, I mean, think of it in this way. So if you have this kind of a lines equation, mx y equal to mx plus c, here your this m and c are the I mean, that is these m and c are enough to define the line, right, where it will lie on the plane. So similarly, these w's are like that. These are like your m and c's. So if you look at this particular uh, Yeah, so if you look at this particular equation, it will be like these are your m's and this is your c. So based on the w's that you generate, the w's that you get, you will be able to draw the line on the decision. I mean, so it doesn't have to be like you have to you first draw a w and then you just orthogonally I mean, to orthogonal to w can draw any line. It's not like that. You'll get the equation of the line from the w's that you get.
So, ma'am, is it correct to say that we will get the entire line using W plus the input data X?
Yeah, correct.
Thank you, ma'am.
Yeah. Okay. So what we wanted to achieve was this the fact that our new w should the dot product of the new w with the this particular data point should be greater than the older one, and this would also mean that we would want our cosine angles to be greater as well for the new one. So cosine cos of alpha new should be greater than cos of alpha. And let's so again let's expand on this a little bit. So cos of alpha nu is what? It's basically if you just plug in the definition of cos of alpha, then it's nothing but alpha nu, sorry, it's nothing but the dot product between w nu and x of t divided by the norms of w nu and x, right? So this is simple. I mean, this is simple. You just break the dot product and that's it. And so now what you do is so again you expand it in this way. So uh, what is w transpose nu? We, if you remember, sorry, I mean w nu, if you remember, it was w plus x. So if you, all you have to do is use that formula again to split this. So similarly, what you, we already saw this in the previous slide. So this gets split to w transpose xt plus xt norm, right? And so if you now suppose you take something like this, that w norm equal to w new norm equal to 1, then all you are left with is something like this. If you you know, put this in the equation and you break it up, then it turns out to be cos of alpha plus the norm of x. Again x cannot be a non I mean, it cannot be a zero vector, so it is cos of alpha plus something positive, which means that this particular thing is greater than cos of alpha. So cos of alpha nu is established to be greater than cos of alpha. And if you go back to again your trigonometry classes, then this particular condition would lead to the fact that alpha nu should be less than alpha. So that is how you have to go about. So these are the conditions. Basically, these are the conditions that one should satisfy. Right. So satisfy for better learning of you know, the model parameter, these w values. So cool. So that is more or less it about perceptron. And now why are, now you will see like the fun where perceptrons are actually used. Perceptrons are actually building blocks inside a neural network. So suppose you have been given some data like this, where so data is always coming in this form. So whatever in machine learning you train, you know that you have a lot of data and you have to train on it. So it will be of this form, that there'll be a pair like this for a classification task, that should be x1 comma y1, x2 comma y2, and dot 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 xn comma yn. So these are all the data points that you have. So this can be, suppose, an image, this can be a piece of text, this can be anything, an audio signal, any other data that you can think of which has a certain label attached to it, y1, y2, yn, and that is how your data set is. And what you want to learn is to learn a mapping from x to y, so that, I mean, given a new x, suppose x what suppose x of something else, some new data point x of new, suppose, then you should be able to predict y of new correctly from whatever data set you have. So now what does a typical neural network look like? So you'll see that this is where, so these are the perceptrons. So this is where I mean, Just a second. Yeah. So you have these. So again, you have the data points. I mean, the this is a single data point where suppose you have a vector like this. These are all vectors: x1, x2, xn. These are all vectors. So these are the individual elements of a certain vector, say x. So you have them as the input, and now what will happen is in a neural network it will be set like this. There will be layers of neurons present, right? And so layers of neurons will be present and they'll be connected by connections like this. So in this layer, suppose there are three neurons. So your x1, I mean your input will be connected to all of these neurons, and this in this layer there are four neurons. This layer again there are four neurons, and at the end you have a single neuron which predicts your output class y. So again we are again for simplicity we are assuming that y uh, is a binary class, binary variable. Yeah. So again for all of these you have weights and biases. So weights and biases are the ones that you want to learn. So for example, um, suppose this particular layer. So basically layer means it's a collection of neurons that are supposed to learn from the data set. So what is a deep neural network? Deep neural network is nothing but uh, the fact that for a I mean you have a model where you have multiple such layers of neurons. So here there are three, for example, one, two, three. There might be many more. So all of these neurons are basically useful. So since you want to, since I mean for example, your data won't be as simplistic all the time where you have a hyperplane like this and neatly all your positive and negative classes are separated based on a line. It might very often happen that you cannot separate your data set. Your even for a binary classification, you cannot separate your data into two parts based on a single line. So that is why you need to learn much more complex patterns, a much more complex hyperplane. So basically a much more complex decision boundary, and that is achieved by neural networks. So what you have is something like this, that in the first layer suppose your learnable parameters are w1 b1, second layer has w2 b2, and third layer has w3 b3. So all of here w1 is a matrix, the b1 is a vector, and similarly for the others. So each of these neurons will have some values, so some weights, scalar weights associated with them. So all of together all of them make up this matrix w1 and the vector b1. So, guys, you should join early. Yeah. Uh, cool. So these are the learnable parameters that you have. So basically, what I mean by this is that these are the parameters that you should learn to learn the mapping from x to y. So trying to make whatever perceptron we learned, that was capable of basically mm, learning a straight line and very comfortably separating positive and negative classes. But in the if you cannot do that, if a straight line is not enough to separate the two classes, you need something more complex, and that is given by the neural network. So suppose at the end of this, I mean what happens here in the first layer is that you get a um, uh, you have your w1 which is matrix. So what you do is this w1 times, I mean this is a dot product, basically w1 dot product x plus b1, and you attach a non-linearity with it. So I'm sure these have been covered in class, so I'm not going to go into what are the details of it. But yeah, this is how it happens, that in the first layer you get a some u1 which is suppose some activation, sigmoid or anything, sigmoid, relu, whatnot. So sigmoid of w1 x plus b1. Similarly, you get here sigmoid of some ReLU or sigmoid of W2 U1. So here basically this, for this layer the input is this layer. So for this layer the input is this layer. So going in that way, for this one the input is the U1. So that is why U2 equal to the sigma of W2 U1 plus B2. So here the parameters were W2 and B2. And similarly you have this W3 B3. So the input to this particular layer is U2. So what you do is you get this particular thing which is basically nothing but W3 into U2 plus B3. So you take the output from here, you take W3 and you do a dot product between not dot product, this is a matrix, sorry, yeah, it was not dot product, my bad. So this is W3 times U2 plus B3, and suppose you call it m of x. So m of x is basically nothing but suppose you want to approximate this entire thing by a function and you call it m of x. So x goes into m and what you get in return is a y value. So suppose I want to ask you guys a question. So yeah, so suppose we are here, right? So basically we want to find out U2, right? And you can see that there are 3 neurons here, right? And there are 4 neurons here. So what would be the dimension of W2? Can anybody tell me? As I said that there are 4 neurons here and 3 here. So
It should be
12.
3 by 4.
yeah, I mean, expand a little bit, like what is the dimension of U1? U1 is a vector. So what is the dimension of U1? Tell me. From this diagram. Don't go deep. Just look at this diagram. U1, you can see there are 3 neurons. So if you think of X, the vector X, the dimension is 3 here. There are 3 elements of X. So how many neurons are there here?
3.
3. So U1 will have a dimension of 3. Similarly, here what you want is for U2 to have a dimension of 4 because there are 4 neurons. And now all you have to do is adjust, like since U1 has a dimension of 3 cross 1, what should you put here so that the output becomes 4 cross 1? So it should be 4 cross 3. So 4 cross 3 of here and 3 cross 1 here, that gives you a 4 cross 1. And similarly your beta parameter will be 4 cross 1. So that's how, I mean, so this is why you should go back to your lectures again and again and try to understand what these individual W's are, how this entire thing happens, because this is a complicated story basically. So now what you want to do is, in order to train your W's, we want some mechanism to, teach the model like how it should set the W's. And that mechanism is basically setting a loss function. So loss function does what? It takes the actual labels that were given to you, this y1, y2 to yn, and it takes the model output. So model output, as I said, is approximated by this m of x. So you have a vector x and you pass it through the function m, and this gives you from here to here direct y, this predicted y basically. So this loss function is a function of both of these, and you basically measure how far away is this predicted uh, y from the actual y. So that is given by this. So suppose we call the predicted y yp. So basically it's a function between yp and the true y. Okay, and what we suppose we measure the distance between these two using some function like MSE, uh, uh, mean square error. And so the MSE is given by this formula, we all know that. So that is what our loss function is, and we can set it to be so many other loss functions. So cross entropy is there, softmax loss is there, so hinge loss is there. So a lot of other loss functions are there which you, so which loss function to set is entirely problem dependent. So Yeah. So now what we'll do is, what we want to do is we have this loss function. This will give us a distance between the predicted value and the predicted y and the true y. Now what to do with it? What we want to achieve at the end of all this is that W1, W2, B1, B2, W3, B3, all these should be trained properly in such a way that you can go from this x to y. So what has been shown mathematically is that so you have to utilize this loss function's value. And how is this loss function minimized? So yeah, so again, one thing I forgot to mention is that since you are measuring the distance between the predicted y and the true y, what would you want? You would want this to match up with this, which means you want it to be as close to zero as possible, this quantity. So basically what we are trying to do here is we are trying to minimize this value. Our optimization problem is that we have to minimize this. Okay. And so in order to minimize this, it has been shown that the minimization happens. So the minimization should happen based with respect to these weights and biases. And that happens when, so these are all, collection of vectors and all. So if you move in the direction of your negative gradient with respect to the loss function, then the loss function gets minimized. So that is how it works. So basically what you have to do is you have your w weights, and you have to basically move to the negative direction of the gradient of these weights based on the loss function. So what we have to do is, for that purpose we have to given an loss function L. What we have to do is we have to find the gradient of that loss function with respect to the individual weight parameters, the W1, W2, W3, B1, B2, B3. Okay, to in order to update the individual weights. So that is what is known as back propagation. This is the mechanism that we use to train our neural networks, right? So what we have to do first is, suppose you want to update W3. So you first compute this del L of del W3, and then you subtract that from W3 in a weighted fashion, which means that you do W3 minus some weight alpha into del of L by del of W3, and that gives you a new W3. So that is yeah, you'll see that later, and I'm sure you have seen something like that in this week's classes also. So some little notes about, so how to find this del of so the crucial thing is that we have to compute what this del of L del of W3 is. So that is basically so while it looks complicated, it can be simplified by just using the chain rule. So if you look at this particular formulation, how it's already given here. Yeah. So what is L? L is your this function, or more precisely this particular function, and you want to reach from L to W3. So you see that L has YP in it and YP has W3 in it. So by the rules of chain rule, all you have to do is first to convert this expression to this expression. So del L of uh, del YP into del YP of the by del W3. So if you, in the interest of time, I'm moving a little bit faster now. So if you compute this particular quantity, you will see that it turns out to be YP into U2, right? And so all you have to, so now that you have found the gradient, all you have to do is you take your W3 and subtract some alpha times this value in order to get your new W3. Similarly, you have a B3 as well. So by the rules of chain rule, you break it again in this form in the same way as this one. And if you do the math by yourself, you'll see that it turns out to be YP. So this is how you, so given a neural network like this is how you update the weights for the final layer. But now, okay, fine. Final layer was a little bit easier. What if we move again even more backwards? We need to update the weights for these two as well. So how do we do that? So again, these are the formulations that we were using, like how we went from X to Y, YP. So these are all given here. And what about the second last layer now? again we have to do the same thing, del L by del W2, and we break it using the chain rule like this. Again all same thing. So if you look at these equations a little bit, it will come to you like how we are breaking this up into using chain rule. And if you so this one we had already calculated. So this one was yp, and this one turns out to be w3, and all you are left to do is find the del u2 by del w2. So what is u2? U2 is this whatever non-linearity is there, or, and w2 u1 plus b2. So moving on, so del of u2 by del of w2. So let's write this expression of sigma of w2 u1 plus b2, and let's call it z, right, just for ease. So now we all know how to differentiate. So this turns out to be the differentiation of this sigma function. So sigma hat of w2 u1 plus b2, which is z basically, and then you go inside. So del of del w2 of this of z basically. So of this w2 u1 plus b2. So now that turns out to be something like this, right? So basically all you have to, this one is trivial to find, so this one will not go into, but all you have to find is the the gradient of this particular activation function. So activation functions, as you must have seen, they tend to vary across networks and applications. So it can be many things like sigmoid, ReLU, and whatnot. So what you have to do is compute these sigmoid gradients from beforehand. So sigmoid is given by this function sigma of z equal to 1 plus 1 by 1 plus e to the power minus z. So all you have to do is, this is actually a pretty easy differentiation. So all you have to do is differentiate this with respect to z in order to get the sigma hat. So that turns out to be something like this. Similarly, if your activation function is ReLU, then you have something like this. So sigma of z equal to max of 0 comma z. This is the ReLU function, and the differentiation likewise turns out to be something like this. So sigma hat of z equal to 0 when z is less than equal to 0. It's 1 otherwise, and so on. So all you have to do for this is that you have to pre-compute this particular value, and the rest is done. So everything has to be, so what you have to do, what are the steps again for back propagation? You do a forward pass. Forward pass means what? Take a data point and propagate it through the network to get your YP basically, sorry. So once you get your YP, you already have the true Y value. So you compute the loss function, and based on the loss function, you all you have to do is you have to calculate the gradient of the loss function with respect to all the learnable parameters, which are W1 to W3, B1 to B3, right? And now once you have computed the gradients, all you have to do is update using the formula that I said. That so if the learnable parameter is W3, its update will be, the new W3 will be the old W3 minus some alpha into this quantity, where alpha is basically the step size or learning rate as we know of, right? Cool. So this is a very short explanation of back propagation. But my suggestion would be that you for your own understanding, you take up even more complex models where you have much more complicated functions than this. And suppose try out the case where instead of MSE you have cross entropy. So that's a tricky one. So try out when the loss function is maybe the network is same, but the loss function is cross entropy. Then you have to work out the math on your own as to what would be the gradient updates for each of the learnable parameters. So that's an exercise for you. So it will go on in the same way. It happens in the chain rule fashion. So the rules are same. The difficulty only lies in how you differentiate, because uh, differentiation is very simple for us when things are all in the scalar space. but now that we are dealing with vectors, so this is a matrix if you remember. So W3 is a matrix. So if you have vectors like this, matrices like this, things become much more complicated. So that is where backprop, that is the difficulty of backprop. So in order to have a good understanding, good grasp of what is going on, I think it's best that you draw a network like this by yourself on your pen, on your paper, and set a loss function of your choice. You can set it to be cross entropy, MSC, whatnot, and you try to solve what would be the gradient updates for W1 and all the WIs and BIs. That will give you a very good understanding of what is going on in the network and how the learning is happening. So do try it out, please. So so that you understand everything in a good way, and yeah, I mean, that will give you a much better understanding of neural networks, because if you don't, then the problem is that you'll everything will be remain fuzzy. So most of the things will remain fuzzy to you. You'll not understand what goes on in the neural network. So please go through these things. So maybe a 5 to 10 minutes of code walkthrough. So basically what we want to do here, again, this is quite fun, where we okay, every time this happens with me only. Anyway, so thankfully the codes were all run. So yeah, so what we want to do is, as I said, we want to do some image classification with a well-known data set called MNIST. So MNIST is something that you will come across many times in your deep learning life, and so the data set is something like this. So you will be give that it consists of images where which consists of handwritten numbers. So it's not together like this. All of these individually, they are all individual images. So this 7, 2, 1, they are all individual images of handwritten numbers, and the task is naturally to identify what is the digit. So the digits always will be from 0 to 9. So 10 numbers, which means 10 digits. So based on this handwritten number, you will have to classify what is the correct class, what is the correct number. So that is something that you have to make your model understand, make your model learn. So that is the goal of this MNIST data set. And some first things first. So this data set is freely available, and I think the code is already given here, so you can also download the data set. So this data, I mean, this handwritten digits are, so number of images for training, I mean, there are 60,000 images available for training and 10,000 available for testing. So one thing that people do is, suppose you have these 60,000 um, images for training, but that might not be enough always. So this is a very simple problem maybe, but when you pick up a much more complicated problem, then I mean, these 60,000 images will never be enough. So what people do is, they do one thing called data augmentation. Augmentation means what? That whatever data has been provided to you, image data particularly, whatever image data has been provided to you, you make small transformations to it, such that you generate a new image from it. So for example, yeah, so here, that is the same thing that they have done here in the first cell. They have tried to, randomly, so they have tried to create some transformations to the input data. This is the input data that is provided. Now we'll try to change it a little bit and increase our data size basically. So one form of that is random erasing, where what you do is you take this image and you image random patches of it. For example, in the result you will see something like this. So the 7 here, this part has become much smaller because that was erased. So the names are self-explanatory actually. So random erasing, random resized crop. So you crop it, resize it. So suppose, so this is some example of that. If you look at this 7, you have resized it, you have tried to make it bigger, but then you have also cropped it a little bit. That is why it looks like it ended too fast. Similarly, random rotation means that you rotate your image by a certain angle, and then Gaussian blur means that you blur your image a little bit. So what you'll do is, this was your original data set. So suppose these constitute of your 60,000 images. Now you'll add all these transformations to your training data. So now it becomes so much more. So 60,000 here, 60,000 here, and so on. So for every image, you'll have such multiple transformations. So for each image, probably you'll get something like four more images. So imagine how much the training data increases because of that. So now so deep models, why do we do this? Because deep models are very, very data hungry. So you'll see when you progress with your class, you'll need so much of data to train the neural networks because they are so much complicated. So whatever I've shown today is actually a very simple uh, formulation of the neural network, but actually they tend to be very, very complicated. Because of that, you need lots of data. So this is a way by which people generally increase their data size. So this is your model architecture basically. So as I said, it's something like this. So as is given in the image here, the input is basically nothing but a vector. So now, because images, images are basically what? How do we perceive them? We perceive them as matrices, basically 2D arrays. So what you do is you flatten them. You flatten the array, you convert it into a vector. So these are all in the MNIST dataset. Images are all 28 cross 28 dimension datasets. So what you do is you flatten them, means you convert this 2D array to a 1D array. So this 28 cross 28 becomes 784. So it's a vector of size 784. So now you have the first layer which has which takes input of dimension 784 and creates 128 neurons where bias is set to true. So this will basically give you W1 and B1. Similarly, this is the second layer which takes as input this 128 dimensional layer FC1, and it will produce, suppose, this 64 dimensional uh, new neurons basically for the second layer. And similarly, on the third layer, you take the 64 generated here and you generate 10 neurons from here. And these 10 neurons you will use to predict your classes from 0 to 9. So that is how. So this code basically, this is a PyTorch code. And so this is how you initialize your network. So first you kind of declare like what are your model parts. So your layers, number of neurons you want in each layer, what activation functions you want to use. So you can see that ReLU was used here. So all the declarations that you want to do to define your network, you have to do in the init part of the class. So you define a model architecture by a class. In the init function, you declare everything, and now how you want to construct the network will be given in the forward function. So the forward function will have the x as the input, which is the image, which was again, if you remember, 28 cross 28, and you reshape that to get the 784 cross 1 vector. So which is what we wanted here. And now what you need to do is you pass this x to FC1, and then you call the activation function to get x1, which is basically u1 here, u1 here. Sorry, and similarly x2 you get in the similar way. So in FC2 you pass x1 and then you generate x2 after passing it through an activation, and then you get the final y, which is FC3 of x2. So this is how you write neural networks. And so these things, yeah, we are out of time today. So data loaders are basically used to organize your data and create batches out of them. So we cannot train the entire data set at one go. So we train them in batches where batch size equal to 128 means that you process 128 images at one go, or something like that. So just the training part I'll explain. And so you get an object of this FC class, which is your model. You have an optimizer which is defined by stochastic gradient descent. So this optimizer is responsible for updating your weights basically. You have the loss function, which is given by cross entropy. So now from epochs, so suppose you want to train your model for 10 epochs. So what you have to do is At each epoch, you ask the train loader to give you the current batch. Batch means 128, any 128 image and label pairs, and in a shuffled way. And now what you do is that is given by your x vector. So x has 128 basically 128 images in it. So you send that x to your model, and the model gives you back your predicted y's. Then you calculate the loss function. That is the next step always. As I said, that you have the true values of y and you have the predicted y's. You calculate the loss function. Then this step basically ensures that all the gradients that were present in your optimizer, they are set to 0. And then you do a back propagation on the loss. So this step basically computes the backprop whatever algorithm that I showed. And then this optimizer dot step, this step basically updates the weights in the way I said. So this is how the training happens. It goes on for 10 epochs. And now what you can do is what is shown here is that you take each x and y from your test loader, again, which will return you data in batches, and you predict the y's from here. And all you have to, because this is the test data, all you have to do is try to match and see what are the predicted, how much match, I mean similarity is there between your true values, true y's, and the predicted y's. So here so epoch 0 to 9, you can see that the test accuracy starts with 90% and steadily it increases till 97%. So that is the test accuracy that we get for this MNIST dataset. So anyway, we'll end here. Uh, so my request would be to, because see, this is a lot of fun. So again, one class is never enough to understand neural networks fully. So my suggestion would be to read blogs, run this code. MNIST is definitely a must do for all neural network beginners. Try to understand this back propagation by setting up challenges for yourself where you change the loss function, change the neural network architecture. So those things will give you very, very clear ideas as to how this entire thing is happening. So unless you get that, you'll not understand what's going on, what will go on in the future classes. So my suggestion would be to go through this very, very thoroughly. And yeah, I mean, you'll have a lot of fun trying to understand this. So fine, we'll end the class today. We
Ma'am, can
Yeah,
you share the links of both the
yeah, yeah, yeah,
PPT
yeah,
and the
yeah,
code?
yeah, yeah. I think so. Yeah, okay, okay. I'll share this. No problem. Fine then. Let's meet next week. Bye.
Thank you.